Yeah, I'm very excited to announce the release of VPI Photonics Design Suite version 11.6. This comes from a lot of market intelligence, but also conversations with our users to put new features, new application examples into the software. So for just a brief introduction about VPI Photonics, we're providing photonic design automation software, so simulation software in the market for over 25 years. And we like to describe our software, and this is what we're always thinking when we're putting new developments in, is that it's integrated. So our photonic integrated circuit design solutions are integrated in the same design environment user interface as our optical system solution. So you can actually do simulations at different levels of abstractions very, very easily. It's also interoperable. So we support Python, MATLAB co-simulation so that you can put your custom models into the software. We also support communication with lab equipment. So we can communicate with AWGs and oscilloscopes as well. So bridging the gap between lab and software. And we claim to be industry leading. And so you'll see firsthand, I'll show some examples of us showing some of the industry leading simulation solutions for new technologies and new technologies that are being proposed. So you can explore those things and understand the trade-offs and the benefits. But we do have software tools that cover various levels of abstraction, from devices, simulating waveguides and fibers, to components, so photonic integrated circuits, also for fiber amplifiers and fiber lasers. And then transmission design, which is more system level simulation. So full optical communication systems, and then even network link engineering. So full fiber network design. But today we're focusing just on VPI Photonics Design Suite. So you can see the tools highlighted in blue there. So VPI Transmission Maker Optical Systems, LabX for interfacing with lab equipment. We support digital signal processing, QKD modeling as well. But also for the fiber optics, fiber amplifiers, photonic integrated circuits, and we even have a machine learning framework. So that's what I'm going to be focusing on today. I'm actually going to switch over to the software. You can see this is the design environment, and I'm not going to read through all of these, but later on, if you want to pause this, you can see a lot of the new features and application examples in the software. Everything from coherent free space optical laser satellite communications, supporting uplink, downlink, ultra wideband transmission for coherent WDM systems, PAM6 modulation, optical DACs, digital analog converters. We even are supporting more electrical modeling. So we are now supporting Verilog A models in the software. So for those who are doing electrical optical co-simulation, new capability. And we have a number of new mode lock laser demos as well. And even some new setups with lab equipment from Keysight's, AWGs, and oscilloscopes. So I'll just show a couple of examples. The first is enabling coherent FSO communication systems. So we have a new coherent FSO channel model. And what's new about this is that it's modeling signal propagation through turbulent atmospheric channels, but it's also now supporting adaptive optics compensation. So we can see how different Zernike polynomials can correct the wavefront aberrations through simulation and coupling into single mode fibers. So what I think is really neat about this is you can really explore, how much compensation do I need from adaptive optics, but then also compare it to digital signal processing. How much of a correction can I get from the DSP chain as well? And so you can compare and contrast and explore those trade-offs. If you just want to see an example of the simulation results, you can see like your constellation before and after DSP for a number of different simulations. So you can see how turbulence through atmosphere changes your constellation diagram. Another quick example, new to the software, is this 800G DWDM system. This is really focused on, it's a representative architecture of NVIDIA's new optical circuit switch that is based on silicon photonic microring modulators. So if you just take a quick walk through the schematic, you can see there's multiple laser channels, so different wavelengths, so 8 different wavelengths in this case. We use this red GUI interface to represent an array of lasers. There's an array of silicon photonic microring modulators as well. Those are connected in series. You have your fiber. You have a demultiplexer over here based on three-ring filters, so photonic integrated circuit components, and then an array of receivers as well. So you can do different things like tune your microring modulators to optimize your performance. You can get an idea of some of the results seen here. So we can look at the optical spectrum before and after the transmitter, the eye diagram, and symbol error rate or bit error rate at different channel positions. So I'm going through these quickly. We do have more information on our YouTube channel about these. If you want a more in-depth peek at some of these simulation examples. Another exciting one, this actually comes from some work from the European project, the ELENA project, where we helped model thin-film lithium niobate modulators and supporting some of the PDK elements that came out of that. This is a coherent system based on optical frequency comb and a thin-film lithium niobate IQ modulator. And so this is really where the excitement is, and is in this IQ modulator. If we look inside of that, you can see it's made up of these photonic integrated circuit components, so MMIs being used as couplers, but these electro-optical phase shifters, which if we take a look at this, you can see this is a new element in the software. So the electrode length is actually made up of multiple segments based on measured S parameters. We can bring in those measured S parameter electrical measurements. We can specify load and source impedance and others. So that's a new component in the software that supports the full system level simulation of an optical transceiver. And then one more example before I wrap up here is, in addition to all the new capabilities for different technologies, we have basic user interface improvements as well. So one of our active models on the photonic integrated circuit side is the photonics TLM model. So you can model lasers with these. It's a very powerful model. It includes Kerr nonlinearities. You can investigate carrier dynamics, spatial hole burning, two-photon absorption. It's a very sophisticated model. One of the challenges with that is that it can also be difficult to use. So we add some ease of use capabilities. This is a multi-section device model. And so in this case, we have an active section. If we want to quickly add an EAM section, we can do that. We can actually visualize the device length as well, upload that, and you can see visually what's going on and how you can make those changes to the device themselves. And then when you click finish, all of those changes graphically get implemented within the model itself. So if you actually look at the parameters, you can see if I look at the device section, there's your active section, your EAM. So it just makes this a little bit easier for those who maybe don't have as much experience with it. But with that, I'm going to wrap things up. And if you're interested, feel free to reach out. There's the sales email. You can email me directly as well. We offer demos. We offer software evaluations of Design Suite 11.6. And coming up at ECOC, we will be running a workshop on simulating data center interconnect systems based on thin-film lithium niobate modulators as well. So follow us on LinkedIn, subscribe to our newsletter. More information is going to be coming up about that, and that will be supported by Epic as well. So yeah, thanks for your attention.